Hey guys, so essentially for this extra credit assignment, I'll be going over the first and second fundamental theorem of calculus that we learned last trimester. So first off, let's start off with the first fundamental theorem of calculus, which essentially states that if a function, so f of x, that also has an antiderivative, let's label it big F of x, from a to b, pardon that A, and is also continuous from a to b, then this essentially applies. The integral from a to b of the normal function of x is going to equal the antiderivative, or big F, of b minus big F of a. Essentially what the first fundamental theorem of calculus is going to do is that it's going to help us better evaluate definite integral questions in the equations. So let's just jump right into a couple examples of how we're going to use this. So let's say integral from 1 to 2 of x dx. So what we're going to do now is this x is essentially going to be our function, f of x equals x. So what the antiderivative of f of x is, or what the integral of x is it's going to be x squared over 2. So now we're going to put the antiderivative into the equation. Squared over 2 from 1 to 2. So now we end up with this. So we have our antiderivative, which is x squared over 2, and we also have the value of a and the value of b up here, 2. So now we're going to plug this into what we have here, f of b minus f of a. So what f of 2 minus big F of 1 is going to equal? It's going to equal 2 squared over 2 minus 1 squared over 2, which is going to be 4 over 2 minus 1 over 2, results in a value of 3 over 2 for this definite integral. Alright, so what I'm going to do now is we'll be looking at a longer definite integral equation and seeing how that pans out with our first theorem of calculus. So we have the question of the integral from 0 to 1 of x to the 6th power minus 2x cubed plus 5x minus 3. So what we're first going to have to do is first antiderive this entire equation and set it to 0 to 1. So what I'm going to do next is I'm going to look at x cubed, which is going to turn into x to the 7th over 7 minus x to the 4th power, and since the 2 here, it's going to be x to the 4th over 2 plus x cubed, and this will be 5 over 3x to the cubed power minus 3x to 0 to 1. So after you found the antiderivative equation for this problem, we're just going to plug 1 in for big F of x, and then plug in 0 for big F of x. So essentially what you're going to get is 1 over 7 for this. For this, it's going to be minus 1 over 2. This is going to be plus 5 over 3. Minus 3. So this is what big F of 1 equals. And then you're going to subtract. Then you're going to put in 0, which is quite simple for this, since x is a part of every expression here. It's going to be 0. So what you're going to be left with is going to be 1/7 minus 1/2 plus 5/3 minus 2. And I think that should equal negative 6 over 7. Alright, so let's give one last example of the first theorem of calculus. And let's use trig this time. So we're going to have the function of sine of x dx from 0 to pi. So what we're going to do, of course, is the same as always. We're going to find the integral of sine to x. And that's going to be negative cosine x. Because the derivative of cosine x should be negative sine x. So this negative should cancel out the other negative. From 0 to pi. Simple enough. And like before, we're just going to plug in pi into this x, and then 0 into this x. So we're going to get negative cosine of pi minus negative cosine of 0. So what cosine of pi is going to be, so just quickly draw this out for you guys. This is pi, this is 0. So looking at cosine, this is going to be negative 1. This is going to be 1. So it's going to be negative, negative 1, minus negative 1. So it's soon going to turn into 1 plus 1. Since these two negatives turn to a positive, these two negatives turn to a positive. And I'm going to get 2 for this definite integral. I think something really neat that we can look at, especially with these trig equations, is that we graph this. If we graph sine of x, sine of 0, it's going to be 0. Sine of pi over 2, that's like 1. Then pi is going to be 1. Essentially what we've done, this equation for this definite integral, is that for this value of 0 to pi, the area under this curve essentially equals 2, and that's pretty neat. Alright, so the last thing we're going to be looking at is the second theorem of calculus, which is going to kind of follow the same constraints as the first one, which is essentially saying that f of x, I believe, continuous from a to b, and there exists an antiderivative big F of x from a to b. Then essentially what we're going to be saying is that f of x and f of x, big F of x, equals integral 0. Actually, wait, not 0, simply any value, so a, to a variable of x, to the function of, let's say, t of dt. So what the second theorem says, that if we derive f prime of x, so we find the derivative of this antiderivative, then what we're going to get is that this x is going to go into the t and simply become f of x. So this essentially is what the rule of the second derivative is. And of course, you also derive d over dx, the value of x. Alright, so let's go over an example of this second theorem of calculus in its making. So what we have is the antiderivative, or big F of x, equals integral from 0 to rad x of cosine of t squared dt. So what we're going to do is we're going to find what the derivative of f prime of x is going to be. So what we're going to do is we're going to put in rad x for t. So it's going to be cosine of rad x squared. Let's put parentheses around this too. Times d over dx, the derivative of rad x. So what we wind up getting is rad x squared is simply going to come out as x. So we have cosine x times, since we have this variable as rad x, we have to find the derivative of it, which comes and turns into 1 over 2 rad x. So what we wind up getting is going to be cosine x over 2 rad x for this second theorem of calculus. And to be honest, that should be about it for the first and second theorem of calculus. Both important concepts to know, but also relatively easy to understand.